In this lesson, we're going to introduce the concept of a limit, which is a central idea to the study of calculus. Now, in order to actually define limits, we're going to need to talk about them in the context of a function. So let me draw on a function first. Now, in order to actually find a limit on a graph like this, we need to choose an x value that we'd like to approach. And now we can go ahead and just introduce the definition to you. A limit is just the value you seem to approach as you move across the graph from either the right or the left. Now, the reason we actually look at the graph on the right and the left is because the graph might do something really unexpected at this point. So even if the function decided to just randomly jump up like this, the limit actually wouldn't change, because as we come in from the left or from the right, it seems as though we're approaching the same point. Now, just to be totally clear, this y value over here is the limit that we seem to be approaching when we get closer to a. On the other hand, this value over here is the true y value we get when we substitute x equals a into f of x. So you just have to realize that f of a doesn't have to be equal to L, although for most functions in most places it usually would be. For example, if you chose a to be over here, the limit would be the same thing as f of a. Now usually in my head, when I picture limits, I kind of imagine this to be almost like a mountainside, and there are two skiers on either side of the slope. Now if this skier is moving to the right and this skier is moving to the left, then you can think of the limit as the point where their skis will collide. Now let's suppose for a minute that we actually change the graph so that they don't collide. Then in this case we just say that the limit doesn't exist and we leave it at that. Now let's imagine for a moment that the position of this right skier is just x. Then of course the position of the skier is just x f of x. So we can just say that this limit L is just what this skier would approach as their x position gets closer to a. And this is actually reflected in the notation. We see that as x approaches a, f of x eventually becomes L in the limit. The cool thing about a limit is that it doesn't need to know what the value is exactly when x equals a. We just need to know what the nearby values are, and that's more than enough to define the limit. Now initially, this might sound like a bit of a useless thing to do, like why not just sub in the value at a? And the reason is because sometimes the value at a is just not defined. To make this a little bit clearer, let me actually give you an example to show you what I'm talking about. So here it looks like we have a reasonably straightforward looking problem. We're asking what f of x seems to approach as x gets closer and closer to 4. Well, we could just sub in 4, right? That would just tell us what value we're approaching. But something goes a little bit wrong. So we can go ahead and just replace every x for a 4. And now if we just look at the bottom, we notice something a little bit bad's happened. 4 minus 4 is just the same thing as 0. Now as we know, dividing by 0 just makes no sense, so that just means that there's no answer, right? Well, not quite. How about instead we try some values close to 4 to see what happens? Now to actually try some values that are close to 4, I'm going to go ahead and use a spreadsheet. Now to begin with, let me label this column x and this column over here f of x. Now I'd also like to draw out a number line over here so that we can track roughly what's going on. Now we're going to want to pick a whole bunch of x values that we'd like to try, where each one gets a little bit closer to 4. Now I was careful not to actually pick 4 because we know that 4 gives us an error. Now we can go ahead and select this cell and then use this value over here and substitute it into the value of f of x. Now since this cell A2 holds the value of x that we're using, whenever we wanted to type in x, we just use A2. Also, SQRT just means square root. Now the great thing about doing this in a spreadsheet is we can actually copy this and do it for all the other cells very, very quickly. So for example, if you clicked on the cell B4, you'd notice this. Before, we had an A2 in this spot, but now since we're on the 4th row, we now have an A4 instead. Now by looking at the numbers we're getting in our spreadsheet, it looks as though the values are getting very close to 0.25. So we think maybe that's our limit, but we should also check it from the other side as well. Now over here I've written that L minus equals 0.25, because we're coming in from the left. Now again, because we're using a spreadsheet, we can just replace all of these values for values coming in from the other side. So we'll start with 5 and then work our way in towards 4 again. So as you can see, the benefit of using a spreadsheet is that the numbers just magically get updated for you. Now looking at the final number, again it looks like we're getting very, very close to 0.25. And now we don't really need the spreadsheet anymore. Now notice that since the value on the left is 0.25 and the value on the right is 0.25, we're justified in saying that the limit of this function is actually 0.25. And of course 0.25 is the same thing as 1 over 4. Now, if you found yourself in a situation where you didn't have access to a spreadsheet, but you had a calculator handy, you could actually use the calculator to find this limit as well. All you really need to do is to test out a value that's very, very close to 4 in this function. So let me just use 4.001. As you can see, when you substitute a value of 4.001 in, the answer you get is incredibly close to 1 on 4 as well. Now I hope this example has shown you something that you didn't expect. Despite the fact that our function is not defined when x equals 4, the limit is perfectly well defined and it's exactly equal to 1 on 4. So it's exactly like this case we have on the left. The value just gets closer and closer to 1 on 4, but when you finally get there, it just disappears. Now the next thing to say is that finding limits in the most general case can actually be pretty tough sometimes. However, as we saw with our calculator, we can usually approximate limits with our calculators. There are courses in maths that can spend a significant amount of time just teaching you how to find limits. However, your first course in calculus doesn't necessarily need you to be super familiar with how to find really crazy, exotic limits. However, there are some specific cases where the limit just doesn't exist. So there are three main situations where a limit just can't exist. The simplest, as we've already discussed, is when both sides of the limit don't agree with each other. In this case, the limit on the left seems to approach this value, which is L minus, and from the right it seems to approach L plus. You can make this happen really easily if you use a piecewise function like this one. So in this case, if you tried to find the limit as f of x approaches 2, on the left it would just be equal to 2, and on the right it would actually be equal to 4. You can test that if you like. Now it's also possible for the limit not to exist when the values are actually infinite. So as you can see, as x approaches a, the values seem to go all the way up to infinity, and that means the limit is also not defined. This can happen on functions like this one as well. Now if you tried to find the limit as this f of x approached 2, you'll also find that the limit is not defined, because both sides seem to approach infinity. And now there's actually one final situation where limits don't exist, and that's when the values oscillate really rapidly. So as you can see with this function, as we get closer to a, the values start to go up and down really quickly. Now whenever this happens, the limit is also not defined, although admittedly this is a bit of an exotic condition. However, there are some functions that display this behavior. This over here is actually my bad attempt at trying to draw this function over here. If you tried actually subbing in random values, you'd see that they don't seem to approach anything in particular, so the limit is just undefined in this case. So the key takeaway here is that the limit L only exists when x approaches the same value from both sides, and that value has to be finite. Now by now you should have a pretty strong intuitive sense of what limits are and how they're defined. But if you actually start searching up limits, you probably come across a definition that really scared my pants off the first time I saw it. So let me go ahead and tell you a little bit about that definition on a new page. Now let's start by bringing back the graph, because we really can't say much without it. Now the so-called rigorous way to think about a limit is very similar to the way we defined it above, but it's also got a little bit of a difference. In this case we're saying that as x gets closer and closer to a, then its y-coordinate on the graph just gets closer and closer to this value L. Now we can write this in the equivalent form that mathematicians actually use to calculate exact limits. So in this case we think that the limit is L, so we're going to try moving away from L by some fixed distance which we'll call epsilon. Now the whole idea here is that I'm trying to bound the y values between L minus epsilon and L plus epsilon. Now as you can see, the graph enters over here and exits over here, so we can go ahead and draw on the x values. So this definition plays out a little bit like this. I start by telling you that the limit of this function is L, and you're a little bit skeptical. So you go ahead and pick a random epsilon of your choosing so that the y value can be anywhere between here and here. If the limit really is L, then I should be able to give you a maximum distance that you can move away from A and still guarantee that the y value never exits this blue square. So to say this again with the letters, you choose a distance epsilon from the proposed limit. This shows me the maximum and minimum y values that you'd like me to give you. And from this I can always give you a number delta that guarantees that the y values will never exit this box over here. So as you can see, between these two x values over here, the y values are fully contained within this box. However, as we said before, we don't care about the value right here. And therefore, we don't allow delta to be equal to 0. Delta actually has to be some number greater than 0. So to make sense of this, let's pick a random point at x. Now we can draw a triangle connecting these 2 points. Now to get this length over here, we just take the x coordinate and then subtract off a. We then take the absolute value because we always want it to be positive. And as we're saying here, we want this distance to be between 0 and delta. So if this distance is just x minus a, then the height of this triangle can be found by finding f of x and then subtracting off L. So the whole idea here is if we want to keep this point inside of this box, if the width of this triangle should always be between 0 and delta, then the height of this triangle should never exceed epsilon. So just to make perfect sense of this, let me actually bring back the last example we did, just to show you exactly how this would work. To begin with, I'll make a graph of f of x just to help you out. So the whole idea here is that we think that the limit is 0.25. So I'm going to go exactly 0.01 units in both directions, so I end up at 0.26 and 0.24. So in this case, our epsilon value is actually 0.01. Now, if you actually use a graphing calculator, you can also find the corresponding x values as well. So on this side over here, we have 3.408, and this side over here, we have 4.694. So you can see that going from here to here would require us to go up by 0.694. And then if we tried subtracting this value from 4, we get 0.592. Now because this value is smaller than this value, we're going to take the value on the left. And therefore we're saying that if we pick a random xy value on this graph, then as long as the distance between 4 and x is less than 0.592, then we're saying that the distance between f of x and 0.25 can never exceed 0.01. Now the main idea is that the limit only exists if we can pick this value to be anything we like, and then from this value we can find the corresponding value of delta. So when you put numbers to this, I hope you can see that it's not really that complicated. We're just saying that this point in here has to stay inside this box for the limit to exist. And with that, we've actually completed our example. Usually, this is called the epsilon delta definition of a limit. So now I'd just like to summarize this lesson. The limit of f of x at a point A is defined as L. We don't actually care what the value is at that particular point, but we only care about what it is as we get closer to this point from the left and the right. We can have situations where the limit is not defined, if for example the graph doesn't meet at one particular point. But if the limit is defined and we say that it's equal to L, then if you choose some random value epsilon, then it has to be possible to find some value delta where this point will never be able to exit this box over here. And this completes our introduction to limits.